Go.
Okay, we're here in the Yukon on July 17th, about midway through a 17,000 to 25,000 kilometer motorcycle ride over North America. The primary purpose of this trip over North America is to investigate water cycling, how water comes from the Pacific Ocean, the Gulf of Mexico, the Atlantic Ocean, and the Arctic Ocean, and falls in this region, subsequently evaporates, and moves on to other regions. Now, to do that, we take water samples in each location and we measure the oxygen and deuterium isotope values of those water samples. Now, the oxygen atoms in a water molecule consist of oxygen 18 and oxygen 16. Oxygen 18 only differs by having 2 extra neutrons. This difference imparts a slightly different physical behavior to that oxygen atom relative to the oxygen 16. So by analyzing the ratio of oxygen 18 to oxygen 16 in water molecules across the country, we can determine how that water has behaved. Basically come up with its history, its origin, whether it comes from the Arctic Ocean, the Pacific Ocean, or the Gulf of Mexico, and how many times it's evaporated along the way. In order to do that evaporation trajectory and the evaporation history, we use the deuterium-hydrogen ratio. Now, just like oxygen 18 and oxygen 16, there are 2 types of hydrogen atom. There's a hydrogen with a single proton, and there's a hydrogen with a proton and a neutron. And because a neutron weighs essentially the same as a proton, deuterium atoms weigh twice as much as hydrogen atoms, plain hydrogen atoms, that is. So by comparing the deuterium to hydrogen ratio to the oxygen 18 to oxygen 16 ratio, we get what's called deuterium excess. This deuterium excess is essentially a record of the number of times this material has evaporated. In this case, the material is water. So the water falls from the sky with a certain isotope value, a certain ratio of oxygen 18 to oxygen 16, a certain ratio of deuterium to hydrogen. It sits in the lake, like this lake, Emerald Lake, here in the Yukon, and either flows away on the surface or through the subsurface, or it can evaporate. Now, when this water evaporates, the oxygen 16s leave more readily than the oxygen 18s, because they're going to vibrate at a higher frequency. Now you have a slow-moving oxygen 18 atom and a fast-moving oxygen 16 atom that's going to tend to fly out of the lake surface, go up into the clouds, and move on to be rained out again. The same goes with the fast-moving or fast-vibrating hydrogen atom and the slow-moving deuterium atom. The fast-moving atom is going to tend to fly out preferentially to the slow-moving one. So that's going to enter the cloud, it's going to join other moisture that's coming from the Pacific mostly, or the Arctic, and move on to fall out into the next lake down the road. Okay, the other thing we're doing here along this trip is part of the route goes over limestone terrain. Now, limestone terrain is simply rock, bedrock in this case, that is calcium carbonate. And in this case, the lake behind me, Emerald Lake, is called Emerald Lake because it's green, emerald green. And this green color is imparted from the calcium carbonate material that is forming in the lake today. This calcium carbonate material is generated or precipitated by algae that live in the lake. In this case, they're charophytes. These charophytes are producing calcite crystals on the outside of the plant body itself. And these tiny crystals refract light such that it gives it the green or blue color that's characteristic of Marl lakes. The important thing about these Marl lakes for our purposes is, whereas we can drive around, collect water samples, and determine the isotope value, this calcium carbonate that forms here today has been forming for the last probably 9,000 years. It's going to lock in the isotope value and the temperature of the lake through time. So we can drive around and collect water samples today. We can get a water sample from this lake, which we have. We're going to analyze that, and then we're going to start looking at the mud. Probably come back here in the wintertime to core this lake when there's ice over the lake, and we can set up our coring rig. That's going to give us a long-term record of isotope values of this lake through history. Again, probably 9,000 years in this case. So we're going to remove a long tube or core of the mud, and then we slice it up millimeter by millimeter, and that's going to give us the secular record of climate variability in the Yukon. Now, if we do that for a number of locations across North America, we can produce a grid of isotope values and isotope variability through time that's going to give us the ability to backtrack atmospheric circulation over the last 9,000 years here, maybe 16,000 years along the East Coast, maybe even a longer period of time down south in the U.S. and in the Midwest. And by understanding how the atmosphere changes today, how the atmosphere changed in the past, we can better predict how the atmosphere will circulate in the future given certain global warming scenarios. The critical thing there is most people are familiar with global warming. It's an anthropogenic enhancement of the greenhouse effect. The greenhouse effect is entirely natural. We need it to keep the Earth warm enough to be habitable. Today, the average mean surface temperature of the Earth is about 15 degrees centigrade or mid-60s Fahrenheit. Without the greenhouse effect, we'd be around zero, maybe below zero. Okay, so it's critical that we have this greenhouse effect. The anthropogenic enhancement that we call global warming is not critical, and it may lead to a lot of problems. We don't know what's going to happen in the future. We don't know that humans are actually influencing the climate significantly. We may exert a significant influence, we may exert very little influence, we just don't know. By evaluating how moisture cycling has varied in the past, we can better predict how moisture cycling is going to vary in the future. Now, in the Midwestern U.S. and the South, people don't want it to get warmer in the summer. Everybody jokes that they want it to get warmer in the winter, particularly here in the subarctic and the Yukon. You hear a lot of people hoping for global warming. You can get bumper stickers that say, we're waiting for it, we want it to happen. But we don't know what's going to happen in terms of precipitation. So it might indeed get warmer here, but it might get drier. It might get much drier, such that this becomes a sub-desert. We just don't know. And one of the most valuable aspects of this particular study is we hope to evaluate that and provide better information to the climate modelers as to what we think will happen.